There is something wrong with the universe. Not wrong in the way a calculation might be off by a decimal point. Wrong in a way that cuts to the foundation of everything physics has ever told us about the nature of reality. Wrong in a way that suggests the cosmos we observe, the one we have mapped, measured, photographed, and built entire civilizations of knowledge upon, may be only one layer of something far larger, far stranger, and far more unsettling than any model we currently possess. The universe should not exist the way it does. That is not a metaphor. It is one of the most rigorously documented crises in the history of modern cosmology, and the scientists who spend their careers working on it do not sleep easily. Because every time humanity has extended its instruments deeper into space, deeper into time, the data has returned a message that our most celebrated theories were not quite right. Sometimes dramatically not right. And right now, at this specific moment in the history of science, the pressure of that incompatibility has reached a breaking point. The universe is expanding. You have probably heard that. It has been expanding since the event we call the Big Bang, approximately 13.8 billion years ago. For most of the 20th century, physicists and cosmologists assumed that this expansion was slowing down. It had to be slowing down. Gravity, the great sculptor of structure across all scales of existence, should be pulling everything back, decelerating the outward rush of galaxies and matter. That was the expectation. That was what every clean model predicted. In 1998, two independent research teams set out to measure exactly how much the expansion was slowing. They used Type Ia supernovae, stellar explosions of such consistent luminosity that astronomers call them standard candles, reliable rulers for measuring cosmic distances. The teams expected to measure deceleration. They measured acceleration. The universe is not slowing down, it is speeding up. Think about what that means. Drop a ball from a building. Gravity pulls it downward, accelerating it toward the ground. That is expected. That is Newton. Now imagine a universe where, the moment that ball leaves your hand, it begins moving away from the Earth faster and faster and faster. Not because of any force you applied, but because space itself between you and the ball is stretching, pushed apart by something that has no name, no detected particle, no direct observation. Something that fills every cubic centimeter of empty space and outmuscles gravity at cosmological scales. That something was named dark energy. And today, according to the best measurements available, it comprises approximately 68% of the total energy content of the observable universe. The matter you can see, galaxies, stars, planets, gas clouds, every atom and every human body that has ever existed, accounts for roughly 5%. Another 27% is dark matter, which we detect only through its gravitational influence on visible matter. We have no confirmed direct detection of a single dark matter particle. The universe is, for all practical purposes, made almost entirely of things we cannot see, cannot touch, and cannot explain from first principles. That is the universe we live in. The observable universe, the sphere of space from which light has had enough time to reach us across 13.8 billion years, spans approximately 93 billion light-years in diameter. 1 light-year is the distance light travels in a single year, approximately 9.5 trillion kilometers. To cross the observable universe from one edge to the other, traveling at the speed of light, 300,000 kilometers per second, the absolute speed limit of physical reality, would take 93 billion years. The current age of the universe is 13.8 billion years. The journey would take 6.5 times longer than the universe has existed. Scale that down to something a human brain can actually grip. If the entire observable universe were compressed to the size of the Earth, the Milky Way galaxy, our home containing somewhere between 100 billion and 400 billion stars, would be smaller than a single grain of sand on a beach that stretches across continents. Not a notable grain. Not a grain you would ever pick out. A grain indistinguishable from the billions surrounding it. And yet, even at that scale, physics tells us the observable universe is not the whole universe. It is simply the part from which light has had time to reach us. The full universe, if it is finite at all, is almost certainly vastly larger. Some current inflationary models suggest the total universe may be at minimum 10 to the power of 23 times larger than the observable portion. Others propose it is infinite, genuinely, mathematically, spatially infinite, containing infinite stars, infinite galaxies, infinite versions of every arrangement of matter that the laws of physics permit. Infinite, not large, not incomprehensibly large, infinite. And this is where the science begins to shift from the merely extraordinary into territory that has forced cosmologists to reckon with the architecture of reality itself. Because if the universe is infinite, or even simply vastly larger than what we observe, then the same laws of physics that produced this specific planet, this specific star, this specific distribution of matter and energy, would produce every possible distribution of matter and energy. An infinite universe does not simply allow for repetition, it demands it. Somewhere, at distances so enormous that no signal will ever cross the space between here and there, the same configuration of particles that produced you is being reproduced, has been reproduced, will be reproduced again. This is not philosophy. This is a direct mathematical consequence of taking inflationary cosmology seriously, and the physicists who developed inflationary theory, including Alan Guth at MIT, who first formalized the inflationary model in 1980, and Andre Linde, who expanded it into what is now called eternal inflation, did not invent this implication as a thought experiment. It emerged from the equations. Cosmic inflation, the extraordinary period of exponential spatial expansion in the first fractions of the first second after the Big Bang, does not appear to have been a single contained event. The mathematics suggest it never fully stopped. It continues in regions of space beyond our observational horizon, producing new volumes of space-time, new universes, each potentially governed by different values of the fundamental physical constants, different laws, different outcomes. That framework has a name, the multiverse. The word gets used loosely. In popular culture, it has become synonymous with science fiction, parallel worlds, alternate timelines, doors between realities. That association has done serious damage to the concept's scientific reputation because the multiverse, as described by inflationary cosmology, is not a story device. It is a prediction. A structural consequence of the same physics that explains the cosmic microwave background radiation, the faint thermal glow left over from the Big Bang, mapped in extraordinary detail by the Planck satellite, and confirmed to match inflationary predictions with precision that would have seemed miraculous to physicists of the mid-20th century. The same physics, the same equations, the same observational framework that gave us GPS satellites, nuclear power, and the detection of gravitational waves, ripples in space-time itself, first detected by the LIGO collaboration in September 2015, predicts that our universe is not alone. But if it is not alone, what does that mean for our universe specifically? What are the boundaries? Can those boundaries be detected? Can they be disturbed? And what does the most recent evidence gathered in the last decade from CMB anomalies, from the deep structure of the cosmic web, from the tension in Hubble constant measurements that has split the cosmological community into competing camps, actually tell us about whether something outside our universe has already left a mark on the one we inhabit? The answers are not simple. They are not settled. They are the active frontier of cosmological research, and they are pointing somewhere that no previous generation of scientists had the instruments, the mathematics, or the courage to seriously consider. Something may have touched our universe from the outside, and the evidence is in the data we have already collected. The cosmic microwave background is the oldest light in existence. It was released 380,000 years after the Big Bang, at the precise moment the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before that moment, the cosmos was an opaque plasma, a dense, superheated fog so thick that photons could not travel freely through it. They scattered endlessly, trapped in a furnace of charged particles. Then, in an event cosmologists call recombination, the fog lifted. The universe became transparent, and the light that had been imprisoned in that plasma flooded outward in every direction simultaneously, filling all of space. That light is still traveling. It has been traveling for 13.8 billion years. It has stretched as the universe expanded from visible wavelengths down into microwave frequencies. Wavelengths roughly 1 millimeter long, invisible to human eyes but detectable by the right instruments. It arrives at Earth from every direction in the sky with almost perfect uniformity at a temperature of 2.725 degrees above absolute zero, 2.725 Kelvin. Colder than any natural environment in the solar system. A whisper from the beginning of time, arriving continuously from everywhere at once. In 1964, Arno Penzias and Robert Wilson at Bell Labs in New Jersey were attempting to eliminate an annoying background noise from a large microwave antenna they were preparing for communications research. They pointed the antenna in every direction. They checked the equipment repeatedly. They famously removed a pair of pigeons nesting inside the horn and cleaned out the accumulated droppings. The noise persisted. It was uniform. It came from everywhere with equal intensity regardless of where they pointed the dish. They had no cosmological explanation for it. Robert Dickey at Princeton University did. He and his team had been building their own antenna specifically to search for the thermal remnant of the Big Bang. Penzias called Dickey. Dickey listened to the description, hung up the phone, and told his colleagues, "We've been scooped." Penzias and Wilson had accidentally discovered the cosmic microwave background radiation without looking for it. They received the Nobel Prize in Physics in 1978. That discovery confirmed the Big Bang framework beyond serious dispute. But it opened a new question almost immediately. The CMB was too uniform. Think about what that means. The observable universe at the time of recombination spanned a region so large that opposite sides of it, the patch of sky where the CMB originates in the direction of, say, the constellation Virgo, and the patch in the opposite direction, toward the constellation Pisces, were separated by distances so enormous that light could not have traveled between them in the time available since the Big Bang. At the speed of light, the two regions had been causally disconnected. They had never exchanged energy, never communicated, never had any physical interaction. And yet the temperature of the CMB coming from both directions is identical to 1 part in 100,000. Two regions that had never touched, that had no mechanism to coordinate, producing the same temperature to 4 decimal places. In physics, that is called the horizon problem. And it is not a minor theoretical discomfort. It is a fundamental violation of what random initial conditions should produce. If you fill 2 identical containers with gas at different temperatures and seal them in separate rooms, they will never reach the same temperature on their own. They require contact, interaction, equilibration. Opposite edges of the early universe had none of that. They should be at different temperatures. They are not. Alan Guth's inflationary model, published in 1980, resolved this with a single radical proposal. In the first moments after the Big Bang, during an interval so short it defies conventional description, somewhere between 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds after the initial singularity, the universe underwent a period of exponential expansion. Not the steady expansion we observe today, an explosive, accelerating stretching of space itself, during which the universe grew in size by a factor of at least 10 to the power of 26, and possibly far more. The entire observable universe today originated from a region smaller than a single proton. That is not a metaphor chosen for effect. A proton has a diameter of approximately 1 femtometer, 1 quadrillionth of a meter. The entire volume of space that would eventually become the 93 billion light-year observable universe began smaller than that. During inflation, that subatomic volume was stretched to macroscopic scales in a time interval so brief that no clock could measure it, and then inflation ended, releasing its energy into the hot plasma of the Big Bang. Because everything in the observable universe emerged from that single, causally connected, thermally equilibrated subatomic region, the uniformity of the CMB is explained. Everything started from the same point. Everything shared the same initial temperature. Inflation stretched that uniform patch to cosmic scales before any differences could develop. The model worked. It explained the horizon problem. It also explained the flatness problem, the observation that the geometry of the universe is spatially flat to extraordinary precision, a condition that standard Big Bang cosmology without inflation would require to be fine-tuned to 1 part in 10 to the power of 60 in the initial moments after the Big Bang. Inflation naturally drives the geometry toward flatness, the same way inflating a balloon makes its surface appear flatter from the perspective of an ant walking on it. And then inflation made a third prediction, one that nobody asked for and nobody expected, and which turned out to be the most consequential prediction in the history of modern cosmology. Quantum mechanics, the physics governing the behavior of matter and energy at subatomic scales, is fundamentally probabilistic. At those scales, physical quantities do not have definite values until they are measured. They exist as probability distributions, fluctuating continuously around average values. These are called quantum fluctuations, and in ordinary circumstances on human scales they are completely negligible. The uncertainty in the position of a baseball due to quantum mechanics is so absurdly small that no instrument will ever detect it. During inflation, those fluctuations were not negligible. They were stretched along with space itself. As the universe inflated, quantum fluctuations in the energy density of the inflaton field, the field responsible for driving inflation, were magnified from subatomic scales to cosmic scales in a fraction of a second. Regions that were infinitesimally denser became large-scale overdensities. Regions that were infinitesimally less dense became large-scale underdensities. These density variations, printed across space by inflation, became the seeds of all cosmic structure. Every galaxy cluster, every filament in the cosmic web, every star, every planet, every atom in every living body traces its origin to a quantum fluctuation stretched to cosmic scale during the first fraction of the first second of existence. The CMB is not featureless. Look at it closely enough. As the COBE satellite did in 1992, as the WMAP mission did from 2001 to 2010, as the Planck satellite did with extraordinary precision between 2009 and 2013, and you find temperature variations at the level of 1 part in 100,000, scattered across the sky in a specific statistical pattern. Hot spots and cold spots, anisotropies. The exact statistical signature of quantum fluctuations stretched to cosmic scales by inflation. The match between the predicted pattern and the observed pattern is one of the most precise agreements between theory and experiment in the history of science. But the Planck data contained something that was not predicted, something that appeared in the temperature map of the CMB and that no standard inflationary model had anticipated. Features in the data that pointed not toward the comfortable, self-contained universe of standard cosmology, but toward something that should not be there at all: a cold spot. In the constellation Eridanus, in the southern sky, there is a region of the CMB that is significantly colder than its surroundings, colder by approximately 70 microkelvins compared to the average CMB temperature. The cold spot, as it is formally known, spans an angular diameter of roughly 5 degrees on the sky. At the distance of the CMB, approximately 46 billion light-years in co-moving distance, that corresponds to a physical scale of several hundred million light-years. Statistical analyses published across multiple studies between 2004 and 2020 have consistently found that the probability of the cold spot arising from standard random fluctuations in a simple inflationary universe is somewhere between 1% and 1 in 10,000, depending on the methodology used. It is not an instrument artifact. The Planck satellite's full sky maps confirmed it with independent measurements. It is real, it is anomalous, and it is large. One proposed explanation is a supervoid, a region of space containing significantly less matter than average, which would cause photons passing through it to lose energy due to the integrated Sachs-Wolf effect, appearing colder in the CMB. A candidate supervoid in the direction of the cold spot has been identified in galaxy surveys. Its properties are disputed, and the most detailed analyses suggest it is not large enough or empty enough to fully account for the temperature deficit on its own. Another explanation has been treated, for years, with extreme caution in the scientific literature. Not because it is obviously wrong, because it is almost too structurally significant to address without extraordinary evidence. The cold spot, in terms of its size, shape, and temperature profile, is consistent with what some theoretical models predict would result from a collision between our universe and another universe during the inflationary epoch. A bubble collision, in the language of eternal inflation. The data that confirmed inflation's greatest triumph may also contain the first observational signature of the multiverse. That possibility is not settled. The scientific community has not reached consensus. But the cold spot is not going away. And the anomalies in the CMB do not stop there. Eternal inflation does not end. That is the core of the problem, and it is worth sitting with that statement long enough to feel its full weight. In Alan Gough's original 1980 model, inflation was a phase transition. The universe tunneled from a high-energy false vacuum state into a lower-energy true vacuum state, and inflation stopped. Clean, contained. A single event with a beginning and an end. The model had a problem, though. The transition was too violent. The energy released during the tunneling would have been distributed so unevenly that the resulting universe would be hopelessly inhomogeneous, nothing like the smooth, structured cosmos we observe. Andrei Linde, working independently at the Lebedev Physical Institute in Moscow, and Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania, each published revised models in 1982 that solved the graceful exit problem. In their new framework, slow-roll inflation, the inflaton field does not tunnel abruptly. It rolls slowly down a potential energy landscape, like a ball rolling down a very gently sloped hill, maintaining the accelerated expansion for long enough to smooth the universe and then reheating it uniformly when the field reaches its minimum energy. The predictions matched the CMB. The flatness problem disappeared. The horizon problem disappeared. The monopole problem, the absence of magnetic monopoles that grand unified theories predicted should be abundant, disappeared. Slow-roll inflation became the standard framework. Then Linde pushed further. In 1983, he published what he called chaotic inflation, and in 1986, eternal inflation emerged as a natural consequence. The argument is not complicated at its logical core, even though its implications are staggering. In quantum field theory, fields do not have perfectly fixed values. They fluctuate. Even the inflaton field, while rolling slowly down its potential energy slope, is subject to quantum fluctuations that randomly kick it upward as well as downward. In regions where the quantum kick upward exceeds the classical roll downward, the field value increases. Those regions inflate faster. They grow larger. They dominate the volume of space. The inflating regions perpetually produce more inflating volume than inflation can consume. Globally, inflation never stops. In any local region, like the patch that became our observable universe, the inflaton field eventually rolls to its minimum and inflation ends, reheating into a hot Big Bang and producing a universe like ours. But that local ending is surrounded by an eternally inflating background that continues expanding and spawning new ending regions indefinitely. Each ending region is a bubble universe, nucleating within the larger inflationary spacetime the way bubbles nucleate in a supersaturated liquid. Each bubble is causally disconnected from all others. The speed at which the inflationary background expands between bubbles exceeds the speed of light, not violating relativity because it is space itself expanding, not matter or energy moving through space, ensuring that no signal, no particle, no causal influence can pass from one bubble to another under normal circumstances. The multiverse is not, in this framework, a speculative add-on. It is the default prediction of the best-tested theory of cosmic origins we possess. Each bubble universe nucleates with potentially different values of the physical constants, the strength of gravity, the mass of the electron, the cosmological constant, the fine structure constant that governs the strength of electromagnetism. These constants are not derived from first principles in any current theory of physics. Their values are measured experimentally and then inserted into equations. String theory, the leading candidate for a unified theory of fundamental physics, predicts that the number of possible vacuum states, each corresponding to a different set of physical constants, is approximately 10 to the power of 500. That number is not a typo. 10 to the power of 500 distinct possible universes, each with its own laws, its own chemistry, its own potential for structure. The string theory landscape, as it is called, maps the territory of all possible physical realities. In most of those universes, life as we know it is impossible. The cosmological constant, the value of dark energy, is fine-tuned in our universe to a precision that has no explanation within standard physics. The observed value is approximately 10 to the power of negative 120 in natural Planck units. Theoretical calculations of what quantum field theory predicts for the vacuum energy density, the energy of empty space that drives the cosmological constant, return a value roughly 10 to the power of 120 times larger than what we observe. That discrepancy of 120 orders of magnitude is the largest unexplained gap between theory and observation in the history of physics. It is called the cosmological constant problem, and it has remained unsolved since Steven Weinberg first quantified it precisely in 1989. 120 orders of magnitude. To grasp that gulf, the ratio of the diameter of the observable universe to the diameter of a single proton is approximately 10 to the power of 42. The discrepancy in the cosmological constant is 10 to the power of 120. It dwarfs the ratio of cosmic to subatomic scales by 78 orders of magnitude. It is, by any measure, the most extreme fine-tuning problem in all of science. The multiverse offers a statistical resolution. If 10 to the power of 500 universes exist, each sampling a different vacuum state, then the overwhelming majority have cosmological constants so large that they expand too rapidly for matter to clump, for stars to form, for galaxies to assemble. A small fraction have cosmological constants so strongly negative that they collapse back in on themselves within fractions of a second. An extraordinarily tiny subset have cosmological constants small enough to permit the formation of structure. We necessarily find ourselves in one of those rare universes, not because the value was designed, but because only in those universes does anyone exist to observe it. This reasoning, called the anthropic principle, formalized by Brandon Carter in 1973 and applied to the cosmological constant by Steven Weinberg in 1987, predicted, 2 years before the discovery of cosmic acceleration, that if the multiverse exists, the cosmological constant should be small but non-zero and positive. It is. The discovery of 1998 confirmed exactly that. Weinberg's prediction is one of the most remarkable in the history of cosmology. Using anthropic reasoning within a multiverse framework, he constrained the value of the cosmological constant to a range consistent with galaxy formation, and the observed value falls within that range. No other theoretical framework had made a comparable prediction. String theory had not. Supersymmetry had not. The multiverse, via anthropic selection, had. The physics of bubble collisions is where the abstract becomes potentially observable. Two bubble universes expanding within the inflationary background will, if they nucleate close enough in time and space, eventually intersect. Their walls, domain walls of energy separating one vacuum state from another, collide. The collision is not gentle. It deposits energy along the boundary where the two bubbles meet, imprinting a specific, calculable signature on the CMB of each bubble. A circular temperature discontinuity. A ring of anomalous temperature, either hotter or colder than the surrounding CMB, with a sharp edge and a specific internal temperature profile predicted by the geometry of the collision. Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Peiris published a systematic search for exactly these signatures in the WMAP CMB data in 2011. They were looking for bubble collision candidates, circular features with the specific temperature profiles predicted by the theoretical models. They found 4 candidate features that passed their statistical filters, 4 possible rings in the CMB consistent with what a bubble collision would produce. Their analysis did not claim confirmation. The statistical significance was not sufficient for that. But none of the 4 candidates could be immediately dismissed, and the cold spot in Eridanus remained the most structurally compelling of all the anomalies. The geometry of a bubble collision imposes a fundamental constraint. Because our bubble universe and the colliding bubble are both expanding spheres within a higher dimensional inflationary space, the intersection of their walls projects onto our CMB sky as a perfect circle, not an ellipse, not an irregular blob, a circle, or a small deviation from circular depending on the relative velocities and nucleation times of the two bubbles. The cold spot has been measured repeatedly for circularity. It is broadly consistent with circular morphology, though the analysis is complicated by the angular resolution limits of current instruments and the contaminating effect of foreground galactic emission. What is not disputed is its anomalous nature. In the Planck collaboration's own analysis of CMB anomalies, published in 2016, the cold spot is listed among a set of features, including the hemispherical power asymmetry, the quadrupole-octopole alignment, and the lack of large angle correlations in the CMB power spectrum, that collectively occur with a probability of less than 1% in standard cosmological models. Each anomaly individually might be dismissed as statistical noise. Their simultaneous presence in the same dataset is harder to dismiss. The Planck team was careful not to overclaim. The language in their papers is precise and restrained. But the data is what it is. The hemispherical power asymmetry deserves particular attention. The CMB, when divided into two hemispheres, shows more temperature fluctuation power on one side of the sky than the other. The effect is subtle, roughly 6 to 7% more power in one hemisphere, but it is present across a wide range of angular scales and has been confirmed in both WMAP and Planck data independently. Standard inflation predicts no preferred direction. Space should be statistically isotropic, the same in every direction. The asymmetry suggests it is not. Something broke the symmetry. Something imposed a preferred direction on the structure of the universe at the largest scales we can measure. A bubble collision would do exactly that. The collision would occur in a specific direction relative to our position within our bubble universe. The energy deposited along the collision boundary would propagate inward, producing temperature and density perturbations that are stronger on the side of our sky facing the collision than on the opposite side. The hemispherical asymmetry, the quadrupole-octopole alignment, and the cold spot all point broadly toward the same general region of the southern sky. The alignment is not perfect. It is not a smoking gun. But it is a pattern, and patterns in physics are how every major discovery in the history of science has begun. The next generation of CMB experiments will either sharpen that pattern into evidence or dissolve it into noise. The Simons Observatory in the Atacama Desert of Chile, currently in the commissioning phase as of the mid-2020s, will measure CMB polarization to sensitivities an order of magnitude beyond Planck. CMB S4, a proposed network of telescopes at both the South Pole and the Atacama, would push sensitivity further still. If the bubble collision hypothesis is correct, the polarization signature at the boundary of the cold spot should have a specific, theoretically predicted structure that temperature measurements alone cannot fully resolve. Polarization maps will either find that structure or not. The universe is not keeping its secrets quietly. It is hiding them in the oldest light that exists, in a pattern of temperatures so subtle that distinguishing signal from noise requires the most precise instruments humanity has ever built. But the pattern is there. It has been measured by independent teams with independent instruments, and it is pointing, with increasing insistence, toward a boundary that should not exist. A place where our universe ends, and something else begins. The data was not supposed to look like that. In 2013, the Planck satellite collaboration released the most detailed full-sky map of the cosmic microwave background ever produced. 1 billion pixels. Temperature measurements across the entire sky at an angular resolution of 5 arc-minutes, fine enough to resolve structures spanning roughly 1/10 of the diameter of the full moon. The map was a triumph of engineering and physics. It confirmed the standard cosmological model, lambda CDM, the model incorporating cold dark matter and a cosmological constant, with extraordinary precision across most of the sky. The acoustic peaks in the CMB power spectrum, the fingerprints of sound waves propagating through the early universe plasma, matched theoretical predictions to better than 1%. And yet, threaded through the data at the largest angular scales, the anomalies persisted. They had been present in the COBE data in 1992. They had been present in the WMAP data through its 9-year mission from 2001 to 2010. Now they were present in Planck, at higher resolution and lower noise than ever before. The hemispherical asymmetry, the quadrupole-octopole alignment, the cold spot, the suppression of large angle correlations, each one confirmed, each one statistically significant. each one lacking a satisfactory explanation within standard inflationary cosmology. The Planck collaboration did something that reflects the highest standards of scientific practice. They published the anomalies prominently, alongside the confirmations. They did not bury the discrepancies. The 2013 anomalies paper and the subsequent 2015 and 2016 analyses laid out the deviations from the standard model with complete transparency, quantified their statistical significance, and acknowledged that their origin was unknown. Unknown. In a dataset representing the most precise measurement of the universe ever achieved. That same year, 2013, a different kind of discovery arrived from a completely different direction, and it reframed the entire conversation about the structure of the cosmos at large scales. The results came from the Baryon Oscillation Spectroscopic Survey, known as BOSS, a component of the Sloan Digital Sky Survey that mapped the three-dimensional distribution of over 1 million galaxies across roughly 1/4 of the entire sky, spanning a volume of space reaching back approximately 6 billion light-years. BOSS was measuring baryon acoustic oscillations, the same primordial sound waves imprinted in the CMB, but now visible as a preferred clustering scale in the distribution of galaxies across cosmic time. The preferred scale, the baryon acoustic oscillation scale, is approximately 490 million light-years. That is the distance that sound could travel through the early universe plasma before recombination froze the pattern in place, and it acts as a standard ruler, a known physical length that cosmologists can measure at different distances to determine how fast the universe has expanded at different epochs. BOSS measured it with extraordinary precision across cosmic history. The results confirmed the accelerating expansion. They confirmed dark energy. They also produced a measurement of the Hubble constant, the current rate of cosmic expansion, that was precise enough to enter into a conflict that had been quietly building for years, and that by the early 2020s had become the most significant crisis in observational cosmology since the discovery of acceleration itself. The Hubble constant is denoted h0. It describes how fast galaxies are receding from us per unit of distance, in standard units, kilometers per second per megaparsec, where 1 megaparsec is approximately 3.3 million light-years. Measure a galaxy 1 megaparsec away, and it recedes at h0 kilometers per second. Measure 110 megaparsecs away, and it recedes at 10 times h0. The value of h0 is the fundamental clock of cosmic expansion, and determining it precisely has been a central goal of observational cosmology since Edwin Hubble first measured it, with significant error, in 1929. Two independent methods of measuring h0 now exist, and they disagree. The first method works in the early universe. It uses the CMB, specifically the Planck satellite's measurements of the acoustic peaks, to fit the full lambda CDM model and infer what h0 must be for the model to match the data. This method is exquisitely precise. The Planck collaboration's 2018 final results give h0 as 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. The second method works in the late universe. It uses a cosmic distance ladder, a chain of overlapping distance measurements beginning with parallax measurements of nearby stars, extending to Cepheid variable stars in nearby galaxies, and then to type Ia supernovae in distant galaxies. The SCHWAR-0ES collaboration, supernovae, and h0 for the equation of state, has refined this measurement across decades. Their 2022 results, led by Adam Rees at the Space Telescope Science Institute, the same Adam Rees who shared the Nobel Prize in Physics in 2011 for the discovery of cosmic acceleration, give h0 as 73.0 kilometers per second per megaparsec, with an uncertainty of approximately 1%. 67.4 versus 73.0. The discrepancy is approximately 5 sigma. In particle physics, 3 sigma is considered evidence. 5 sigma is the threshold for a discovery. A 5 sigma discrepancy between two independent, mature, carefully cross-checked measurements of the same fundamental constant is not a rounding error. It is not an instrument calibration issue. Both teams have spent years examining every possible source of systematic error. The discrepancy has not gone away. It has grown stronger as measurements improved, when naive expectation would have been that increasing precision would cause the two values to converge. This is called the Hubble tension, and it is, as of the mid-2020s, the most precisely quantified anomaly in all of cosmology. The implications are severe. If both measurements are correct, and no compelling systematic error has been identified in either, then something is wrong with the standard cosmological model. Lambda CDM, in its standard form, cannot simultaneously produce a CMB that matches the Planck data and a late universe expansion rate that matches the distance ladder. The model works extraordinarily well across an enormous range of scales and phenomena. But the Hubble tension is a hairline fracture in its foundation, and hairline fractures in physics have historically been the entry points through which entire new frameworks have entered. Proposed solutions to the Hubble tension are numerous and varied. Early dark energy models, in which an additional energy component was active in the universe just before recombination, modifying the sound horizon and shifting the inferred CMB value of H0, have attracted significant theoretical attention. Interacting dark matter and dark energy models, modifications to general relativity at cosmological scales, extra-relativistic species in the early universe, and decaying dark matter scenarios have all been explored in the peer-reviewed literature. None has achieved consensus. None simultaneously resolves the Hubble tension without creating new discrepancies elsewhere in the data. One class of solutions points back, once again, toward the structure of the inflationary epoch. If the inflationary dynamics that produced our observable universe were not perfectly smooth, if there were features in the inflaton potential, or if the reheating process after inflation was not instantaneous, the resulting modifications to the primordial power spectrum could propagate through cosmic history and manifest as precisely the kind of tension we observe between early and late universe measurements. The Hubble tension, the large-scale CMB anomalies, and the cold spot may not be independent puzzles. They may be different faces of a single underlying departure from the simplest inflationary scenario. The most dramatic version of that departure involves the topology of the universe itself. Topology is distinct from geometry. Two spaces can have the same local geometry, the same rules for measuring distances and angles, while having completely different global topologies. A flat plane and a flat torus have identical local geometries. Both are locally flat, obeying Euclidean rules. But a torus wraps around on itself. Travel far enough in one direction, and you return to your starting point. Standard cosmology assumes the universe has trivial topology, that it simply extends indefinitely in all directions without wrapping. But this assumption has never been observationally tested to large scales. Jean-Pierre Luminet and collaborators published a paper in Nature in 2003 proposing that the universe might have the topology of a Poincare dodecahedral space, a specific non-trivial topology in which opposite faces of a dodecahedron are identified. In this model, the universe wraps around on a scale slightly larger than the observable universe, and light from distant objects could wrap around the topology to reach us from multiple directions. This model made a specific prediction. The quadrupole and octupole moments of the CMB, the largest scale temperature fluctuations, should be anomalously low and should show specific alignments. The quadrupole and octupole moments are anomalously low. They do show specific alignments. The axis of the quadrupole and octupole is aligned with the ecliptic plane, the plane of Earth's orbit around the Sun, a coincidence so improbable in a standard infinite universe that it has been called the axis of evil by cosmologists Kate Land and João Magejo in a 2005 paper that gave the anomaly its enduring nickname. The Poincare dodecahedral space model was subsequently challenged on statistical grounds, and the debate over cosmic topology remains open. But the alignment of the largest CMB structures with the geometry of our local solar system is precisely the kind of feature that should not exist in a universe whose structure is generated by random quantum fluctuations. Random processes do not know where the Earth is. They do not preferentially align their largest scale features with our orbital plane. Something produced that alignment. Its origin is unknown. Every anomaly points to the same conclusion. The universe at its largest observable scales departs from what the simplest models predict, and every departure, examined carefully, opens the same door. a door that standard cosmology has no mechanism to explain from within its own framework. The physics that accounts for everything from the formation of hydrogen in the first minutes after the Big Bang to the clustering of galaxies across billions of light years fails, specifically and repeatedly, at the scale where our observable universe ends and the unknown begins. Not at small scales, where quantum gravity effects might be expected to complicate things. Not at intermediate scales, where the complexity of astrophysical processes could introduce confusion. At the largest scales. At the boundary, where, if eternal inflation is correct, the wall of our bubble universe sits. The James Webb Space Telescope launched on December 25, 2021, and by the summer of 2022, it had already broken something. Not an instrument, not a mirror segment. It broke an assumption, one so deeply embedded in the standard cosmological model that most working cosmologists had stopped thinking of it as an assumption at all. Webb began returning images of the early universe at redshifts above 10, corresponding to a period less than 480 million years after the Big Bang. At those distances, at that age, the universe should contain only the earliest, smallest, most primitive galaxies, diffuse, irregular proto-galactic structures slowly assembling their first generations of stars from primordial hydrogen and helium. What Webb found instead were massive, fully formed, morphologically mature galaxies. Galaxies with stellar masses reaching tens of billions of solar masses. Galaxies with established disk structures. Galaxies so large and so well developed that according to every galaxy formation model calibrated on standard lambda CDM cosmology, they should not exist yet. The universe at the age Webb was observing had not had enough time to build them. One solar mass is approximately 2 times 10 to the power of 30 kilograms. The stellar mass of the Milky Way is estimated at between 50 billion and 60 billion solar masses, accumulated over roughly 13 billion years of star formation. Webb was finding galaxies approaching that mass at cosmic ages of 300 to 500 million years. Structures of comparable complexity to our own galaxy, assembled in a time frame shorter than the time it takes the solar system to complete 2 full orbits around the galactic center. The 2023 paper by Ivo Labe and collaborators in Nature, analyzing Webb's first deep field data, identified 6 candidate massive galaxies at redshifts between 7.4 and 9.1, all with stellar masses between 10 billion and 100 billion solar masses. The most extreme of these, if confirmed, would represent a stellar mass density in the early universe, roughly 9 times higher than the maximum predicted by the most optimistic galaxy formation models. The authors themselves described the tension with lambda CDM as profound. Galaxy formation depends on dark matter. In the standard model, dark matter halos collapse first under gravity, and baryonic matter, ordinary matter made of protons, neutrons, and electrons, falls into those halos, cools, condenses, and forms stars. The process takes time. The dark matter halo must reach sufficient mass. The gas must cool below a threshold temperature. Star formation proceeds at a rate constrained by the available gas supply and the feedback mechanisms, supernovae, radiation pressure, stellar winds, that regulate it. The physics is well understood. The models are sophisticated. They have been tested against galaxy surveys reaching back to redshifts of 3 and 4 with extraordinary success. At redshifts above 10, in the window Webb opened for the first time, those models are failing. Several explanations have been proposed. The simplest invokes enhanced star formation efficiency in the early universe. The possibility that early galaxies converted their available gas into stars at rates substantially higher than galaxies do today, bypassing some of the feedback-limited regulation that constrains modern star formation. This explanation is conservative. It requires no new physics, only a modification of the parameters governing processes already in the model. A more structurally significant explanation involves the nature of dark matter itself. Standard cold dark matter, particles moving slowly compared to the speed of light, clustering on all scales down to subgalactic sizes, makes specific predictions about the abundance and internal structure of dark matter halos at high redshift. If dark matter is instead warm or fuzzy, or if it decays, or if it interacts with ordinary matter in ways not yet detected, The halo mass function in the early universe could differ dramatically from the standard prediction, potentially allowing the rapid assembly of the massive structures Webb is observing. The most radical explanation touches the foundations of inflation itself. If the primordial power spectrum, the distribution of density fluctuations that inflation imprinted on the early universe, had more power at small scales than the simplest inflationary models predict, structure could form earlier and more rapidly than the standard model allows. Enhanced small-scale power is, in fact, a prediction of certain classes of inflationary models with features in the inflaton potential, the same features that could modify the CMB power spectrum at large angles. The same features implicated in the Hubble tension. The anomalies are converging. Webb's massive early galaxies, the Hubble tension, the CMB large-scale anomalies, the cold spot, the hemispherical asymmetry, each of these was discovered independently by different teams, using different instruments, measuring different physical quantities across completely different scales and epochs of cosmic history. They are not the same measurement made multiple times. They are different windows cut into the same structure, and each window is showing the same crack. The gravitational wave background adds another voice to this convergence. In 2023, multiple pulsar timing array collaborations, Nanograv in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array, simultaneously announced the detection of a stochastic gravitational wave background permeating the universe. Gravitational waves at nanohertz frequencies with wavelengths spanning light years, arriving continuously from all directions. Pulsar timing arrays detect them by monitoring the precise arrival times of radio pulses from millisecond pulsars, neutron stars spinning hundreds of times per second with rotational stability rivaling atomic clocks. A passing gravitational wave stretches and compresses the space between the Earth and a pulsar, introducing tiny correlated delays in pulse arrival times across the array of pulsars on the sky. The signal was real. Its statistical significance exceeded 5 sigma. The correlation pattern across pairs of pulsars matched the Hellings-Downs curve, the specific angular correlation predicted for a gravitational wave background, with high confidence. This was the first direct detection of gravitational waves at cosmological scales, complementing the LIGO and Virgo detections of gravitational waves from individual compact binary mergers at much higher frequencies. The most straightforward source of a nanohertz gravitational wave background is a cosmic population of supermassive black hole binaries, pairs of black holes, each containing hundreds of millions to billions of solar masses, orbiting each other in the centers of merging galaxies across cosmic history and slowly spiraling inward as they radiate gravitational wave energy. This astrophysical explanation is well motivated and likely contributes to the observed signal. But the amplitude of the detected background is higher than many astrophysical predictions expected, and some analyses find spectral features, deviations from the simple power law spectrum expected from a pure binary population, that have attracted theoretical attention. Among the alternative or additional sources considered in the peer-reviewed literature, a gravitational wave background produced during a first-order phase transition in the early universe, during which regions of different vacuum states nucleated and their walls collided, producing a stochastic background of gravitational radiation, bubble wall collisions. In the context of the gravitational wave background, those bubbles are phase transition bubbles in the early universe plasma, not the inflationary bubble universes of eternal inflation. The physics is different, but the mathematical machinery is related, and the detection of a potentially anomalous gravitational wave background has reopened in a completely different observational channel, questions about the dynamics of the early universe that the CMB alone cannot settle.
The Laser Interferometer Space Antenna, LISA, is scheduled for launch in the mid-2030s. LISA is a space-based gravitational wave detector consisting of 3 spacecraft separated by 2.5 million kilometers, forming an equilateral triangle in space trailing the Earth in its orbit around the Sun. The arm length alone, 2.5 million kilometers, is approximately 6.5 times the distance from the Earth to the Moon. LISA will be sensitive to gravitational waves at millihertz frequencies, bridging the gap between the nanohertz regime of pulsar timing arrays and the 100 Hz regime of LIGO.
At millihertz frequencies, LISA will be directly sensitive to gravitational wave signals from cosmological phase transitions, from cosmic strings, topological defects that some inflationary models predict, and potentially from processes occurring at energy scales approaching those of inflation itself. If the early universe underwent a first-order phase transition, if space itself cracked and bubbles of a new vacuum state nucleated and expanded and collided, LISA will hear it. The Roman Space Telescope, formerly known as WFIRST, will survey the large-scale structure of the universe across an enormous volume with a sensitivity to the dark energy equation of state that surpasses all previous instruments. Its measurements of weak gravitational lensing, the subtle distortion of background galaxy shapes by the mass distribution of foreground structure, will map the growth of cosmic structure across time with a precision that will either confirm the Standard Model's predictions or reveal deviations pointing toward new physics. The Vera Rubin Observatory, conducting the legacy survey of space and time across a 10-year baseline beginning in the mid-2020s, will catalog billions of galaxies, mapping baryon acoustic oscillations, weak lensing, and the distribution of matter across a volume of the universe so large that the resulting dataset will take years to fully analyze. All of these instruments are pointed at the same question from different angles. The question is not whether the universe is surprising. It is. The question is whether the surprises are connected, whether the Webb galaxies, the Hubble tension, the CMB anomalies, the gravitational wave background, and the topology of the universe's largest structures are symptoms of a single underlying departure from the Standard Model, or a collection of independent flukes that will each eventually be explained away. The flukes have not been explained away. They have multiplied. Each new instrument, each new dataset, each new analysis has added detail to the same pattern rather than dissolving it. And the pattern, read in its entirety, describes a universe that is not the smooth, infinite, featureless extension of standard cosmological assumptions. It describes a universe with a history, a universe that began in a specific way, in a specific place within a larger structure, shaped by dynamics that extended beyond the moment of its own Big Bang. A universe whose oldest light carries the memory of something that happened before it was transparent enough to carry any light at all. A universe whose largest structures whisper, in temperature gradients measured to 1 part in 100,000, about a contact it may have made with something outside itself. The instruments are listening, the data is accumulating, and the universe, patient, indifferent, ancient beyond any meaningful human analogy, is answering. Somewhere in the Atacama Desert, at an altitude of 5,100 meters above sea level, the air is so thin that a person without acclimatization loses consciousness within minutes. The water vapor content is so low that the atmosphere becomes nearly invisible to millimeter wave radiation. It is one of the driest places on the surface of the Earth, and it is precisely this hostility to biological comfort that makes it ideal for cosmology. The Atacama Cosmology Telescope has been operating there since 2007, measuring the polarization of the cosmic microwave background with a sensitivity that was, for most of human history, not merely unachieved, but unimagined. Polarization is the orientation of the electric field oscillations carried by a light wave. The CMB is not perfectly unpolarized. The same acoustic oscillations that produce the temperature fluctuations also produce subtle polarization patterns, imprinted at the moment of recombination and preserved in the microwave background for 13.8 billion years. Those polarization patterns carry information that temperature measurements alone cannot extract. They encode the geometry of the scattering events that release the CMB photons. They carry the E-mode patterns produced by density fluctuations, and the B-mode patterns that, at primordial scales, can only be produced by gravitational waves, specifically by the gravitational waves generated during inflation itself. Primordial gravitational waves from inflation have not yet been detected. Their amplitude is parameterized by a quantity called the tensor-to-scalar ratio, denoted R. Current upper limits from the BICEP and Keck array experiments at the South Pole constrain R to be less than approximately 0.036. That upper limit is already scientifically meaningful. It has ruled out entire classes of inflationary models that predicted large gravitational wave amplitudes. The next generation of experiments, including the Simons Observatory and CMB-S4, will push sensitivity to R values below 0.01. If inflation occurred at the energy scales most theoretically favored, a detection is within reach. A detection of primordial gravitational waves in the CMB polarization would be, without exaggeration, among the most significant experimental results in the history of science. It would confirm that quantum fluctuations in the fabric of spacetime itself, gravitational waves generated at energy scales approaching 10 to the power of 16 giga-electron volts, energies that no particle accelerator ever built has approached and none planned will approach, were stretched to cosmic scales during the inflationary epoch and persist today as a faint imprint on the oldest light in existence. It would confirm that the quantum nature of gravity was physically relevant at the birth of the observable universe. It would also tighten the constraints on eternal inflation. Not all inflationary models produce eternal inflation. The ones that do have specific relationships between the scalar spectral index, the tilt of the primordial power spectrum, already measured by Planck to extraordinary precision, and the tensor to scalar ratio. A measurement of R would map more precisely which region of inflationary model space is physically realized, and whether that region generically produces eternal inflation, and therefore whether the multiverse is a necessary consequence of the physics that created our universe, or merely a possible one. The word necessary carries enormous weight in physics. A theory that merely permits a phenomenon is interesting. A theory that requires it changes everything. Quantum mechanics does not merely permit superposition, it requires it. General relativity does not merely permit curved space-time, it requires it. If the inflationary framework, constrained by the full suite of CMB measurements, temperature, polarization, the tensor to scalar ratio, the non-Gaussianity of primordial fluctuations, converges on a model that necessarily produces eternal inflation, then the existence of other universes becomes as demanded by the data as the existence of dark energy, not observed directly, but required by the physics that is observed directly. That is a different epistemic status than speculation. Physicists do not directly observe quarks. They are permanently confined inside hadrons, invisible to any conceivable direct detection. Their existence is inferred from the behavior of protons and neutrons in particle accelerators, from the patterns of jets in high-energy collisions, from the success of quantum chromodynamics in predicting scattering cross-sections to many decimal places. The inference is so robust, so multiply-confirmed, so deeply woven into the successful predictions of the standard model of particle physics that no serious physicist doubts quarks exist. The multiverse may be approaching asymptotically a similar epistemic status, not proven, not directly observed, but increasingly required by a framework whose other predictions keep coming true. The observable universe contains, by current estimates, approximately 2 trillion galaxies. The 2016 study by Christopher Consolis and collaborators, using deep field observations and models of galaxy evolution, revised the previous estimate of 100 billion galaxies upward by a factor of 20, accounting for the galaxies too small and too distant to be directly imaged by telescopes of that era. 2 trillion galaxies, each containing, on average, hundreds of billions of stars. Each star, statistically, orbited by planets. The Kepler Space Telescope mission, operating from 2009 to 2018, established that planets are not exceptional companions to stars. They are the rule. The Milky Way alone likely contains more planets than stars, with estimates ranging from 100 billion to 400 billion planetary bodies in our galaxy alone. On one of those planets, around one of those stars, in one of those 2 trillion galaxies in this specific universe, matter organized itself into structures capable of measuring the temperature of light that has been traveling since 380,000 years after the beginning of time. Capable of detecting the stretching of space-time by fractions of a proton's diameter, capable of reading, in the polarization pattern of microwaves arriving from every direction simultaneously, the gravitational echo of the first fraction of the first second of existence. That capacity, the capacity of the universe to produce instruments that measure itself, is not a given. It depends on the values of the physical constants being within the narrow range that permits chemistry, that permits stable atoms, that permits planetary formation, that permits biological complexity. The cosmological constant being what it is, rather than 10 to the power of 120 times larger. The fine structure constant being what it is, rather than a value that would prevent electrons from forming stable atomic orbitals. The ratio of the electromagnetic force to gravity being what it is, rather than a value that would cause all stars to either burn out in thousands of years or never ignite at all. Whether those values reflect the anthropic selection of observers within a multiverse or a deeper principle of physics not yet discovered or something else entirely, that question is not settled. It may not be settable by current methods. But it is a real question, asked by physicists using real mathematics, and the universe's answer is encoded somewhere in the data already collected, or in the data that instruments already built or under construction will collect within the next 2 decades. The cold spot remains cold. It has been measured by COBE, by WMAP, by Planck. It will be measured by the Simons Observatory and by CMB-S4 with polarization sensitivity that will either find the specific boundary signature of a bubble collision or constrain its amplitude below any theoretically motivated threshold. One of those outcomes will happen. The data will arrive. The universe does not withhold its measurements indefinitely. The Hubble tension remains, 73 versus 67. The distance ladder measurements are being independently cross-checked using gravitational wave standard sirens, binary neutron star mergers detected simultaneously in gravitational waves, and electromagnetic light, which provide a completely independent method of measuring cosmic distances without any of the calibration steps of the traditional distance ladder. The 2017 detection of GW Sun 70817, the neutron star merger observed by LIGO, Virgo, and dozens of electromagnetic observatories simultaneously, produced the first standard siren measurement of H0. Its precision was limited by the single event. Dozens or hundreds of such events, accumulated over the coming decades of gravitational wave astronomy, will produce a standard siren value of H0 with percent-level precision. If it agrees with the distance ladder at 73 and disagrees with the CMB at 67, the standard model is broken. A replacement will be required. Replacements in physics are not catastrophes. They are the mechanism by which physics advances. Newtonian gravity was not wrong. It was a limiting case of general relativity, accurate within its domain, and superseded only where its domain ended. The standard cosmological model is not wrong about what it successfully predicts. It will be superseded, if it is superseded, only at the scales where its predictions fail, at the largest scales, at the earliest times, at the boundaries of the observable universe, at the interface between what we can measure and what we can only infer. At those boundaries, the universe is speaking clearly enough to be heard. The signal is in the temperature maps, it is in the polarization patterns, it is in the clustering of galaxies across billions of light years. It is in the arrival times of radio pulses from spinning neutron stars distributed across the Milky Way. It is in the spectra of the most distant galaxies James Webb can resolve. All of it, taken together, describes a cosmos that is not the simple, smooth, featureless infinite space of the most naive model, but a universe with structure at every scale, with anomalies at the largest scales, with a history that may extend beyond its own beginning, embedded in a larger framework whose nature is the central open question of 21st century physics. 13.8 billion years ago, in a region smaller than a proton, something happened. Space expanded. Matter and energy emerged. Atoms formed, stars ignited, galaxies assembled, planets condensed from cooling disks of gas and dust. And on at least one of those planets, the matter that the universe made looked back at the universe that made it and began to ask what else was out there. The question has no final answer yet, but the data is coming.